So, I mean you recall whatever we have discussed during the course of the last few weeks, we have seen various ways of designing digital circuits and systems, combination circuits, sequential circuits, simple, very simple circuits, slightly more complex circuits. Now, one thing you should remember, whenever we are trying to design high performance systems where the speed of operations and something called throughput, number of calculations that you are able to do per unit time, that becomes important, we often go for a technique called pipelining. So, we shall be looking at several examples of pipelining, how we can model pipelines in Verilog and so on. But in this lecture, let me give you a very brief overview about the basic concepts in pipelining, what it is and how does it give us an advantage in terms of speed up and increase in throughput. Okay. So, the topic is basic pipelining concepts. Now, what is pipelining? Pipelining essentially is a method for overlapped execution of several input sets. Like what I mean to say is that you see, whenever you have some kind of computation, something you want to compute, there will be some input data you are applying and you are finally getting some result. Now, your computation may be such that you have to do the same kind of calculation on a large number of input data. So, the data are coming one after the other. Okay. So, in that case what we are saying is that the computations that are going on for the consecutive data items, they are somehow overlapping in execution. Because you see, conventionally without pipelining what we will do, first data comes, we finish our computation, generate the result, then only we take the second input. Again we do the computation, generate result, then we take the third input. There is no overlap. Now, what I am saying is that before the computation on the first data is complete, we have already started something on the second data. This is something which is called overlapped execution. We shall see how. So, this overlapping normally we just express in terms of something called sub computations or stages. Well, I shall be explaining through some examples. So, what you are saying is that we have some computation, let us say we represent it like this, and as an alternative we divide the computation into smaller pieces called stages. Let us say there are k number of stages. This is how what we are doing the partitioning, right. Now, in this kind of a partitioning, the way pipelines are implemented, the cost of implementation does not increase appreciably, very low increase. But the advantage is that we shall see how it comes. The speed up can be very significant. It will almost be equal to k, how many times we have divided the computation into the number of partitions. Now, in a computer system, pipelining can be used to speed up operations in various different places. When instructions are executed, this is called instruction execution. When some computations are going on, let us say arithmetic computations, addition, subtractions, multiplications, there also we can use pipelining to speed up, and memory access. When a large number of memory accesses are going on consecutively, using pipelining again we can speed up the overall access time of the memory using some efficient technique. Okay? Fine. Let us take a real life example to illustrate how pipelining helps. This is nothing to do with a computer system or a digital system. Let us take this rectangular box indicates some operation that you are doing. What is the operation? This corresponds to a machine M, let us say, which can wash, dry and iron clothes one at a time. Suppose you have manufactured such a machine which will take one cloth at a time, it will automatically wash, dry and iron, and it will give you the nicely ironed cloth as the output. Let us say the total time taken for this W, D and R steps all taken together is T, capital T. So, if we have n number of clothes, so how much time will it take total to complete for all the n? For every cloth we need T. So, for n clothes we need n multiplied by T. This we represent as T1, means I have a single partition, 1 is that 1. Now, let us say that you have thought that instead of a single machine doing everything, because you see anyway washing, drying and ironing are 3 different things. Washing involves soap and water, drying involves heater, blowing air and so on, and ironing involves pressing and so on. So, there is nothing which is repeated in these steps, they are as such different. So, you identify that, and what you come up with that? Well, let us now do this. Let us divide this machine into 3 smaller machines, one which can only wash, second which can only dry, third which can only iron. Well, now you can argue that because we have divided the functionality and there is very little overlap, the total cost does not increase appreciably. Of course, there will be a little increase in cost, because you have to do a necessary packaging, you have to put it inside a nice cabinet and so on. But whatever is there inside the actual electromechanical systems, they are not much different. So, we split the machine into 3 smaller machines, MW, MD and MR, these 3 boxes which can perform specific tasks. Now, here what happens, let us see. Now, the total time was T. Let us say now this individual stages, they will take 1/3 time each, T by 3, T by 3, T by 3. So, the total time is still T. Now, see, when a cloth comes, you wash it. After washing is complete, you give it for drying. Now, you see, while drying is going on, this washing machine is free. Now, the second cloth can be given for washing. Similarly, when the first cloth goes for ironing, the second cloth can come for drying and the third cloth can go for washing. So, I will show you how. If we have a mechanism like this is called pipelining, as if there is a pipe. The clothes are flowing through a pipe and there are 3 stages. It first goes to W, then to D, then to R, and then it goes out. So, we will see how this calculation comes. For n clothes, the total time taken here will be 2 plus n multiplied by T by 3. So, in the first case, the time was n multiplied by T, and in the second case with 3 stages, the time is coming as 2 plus n into T divided by 3. Let us assume that the value of n is very large. Let us say, for example, I am washing 1000 clothes. So, with respect to 1000, you can ignore this 2 is negligible. So, what you can say? You can say that your T3 is approximately 1/3 of T1. T1 was NT, T3 is approximately NT divided by 3. So, you have gained a 3 times speed up without investing on 3 machines. You see, to get a speed up of 3, what you could have done initially, that big machine you could have bought 3 copies, which means you would spend money 3 times the cost. But now you have not done that, you have divided that big machines into 3 parts. It will involve a marginal increase in cost, but still the performance is improving 3 times. This is the essential idea behind pipelining. Without increasing the cost appreciably, we are getting very appreciable speed up. Okay? Now, let us see how this is coming. Let us look at the axis of time. This is washing, drying and ironing. So, cloth 1 comes here, cloth 1 comes for washing. So, it takes T by 3 time. After T by 3, cloth 1 comes for drying and the second cloth comes for washing. This requires again T by 3, then cloth 1 comes for this ironing, cloth 2 for drying, cloth 3 for washing. Now, after T by 3 cloth 1 is done. So, cloth 1 you can take out, then cloth 2 comes here, cloth 3 comes here, cloth 4 comes here. After T by 3 cloth 2 can be taken out, then cloth 3 can be taken. You see, after this pipe is full, after every T by 3, T by 3, T by 3 time you can take out 1 cloth. So, 1 cloth per time T by 3 is being generated as output, right. So, for 1 cloth, the first cloth will take T by 3, T by 3, T by 3, 3 into T by 3. Second cloth will take 1 more time, 1, 2, 3, 4, 4 into T by 3. Third cloth will take 5 into T by 3. So, proceeding in this way, the nth cloth will take 2 plus n T by 3. That is what we showed in the expression. Now, extending this concept to a processor, suppose I am building a computer, I want to speed up instruction execution, that is called a processor pipeline. Okay. So, instead of executing one instruction at a time, I am dividing the total execution process into stages and I am overlapping the execution in the same way. So, here again I am just repeating. So, we had 2 alternatives. One is we can repeat the or replicate the hardware k times, which also will increase a k times increase in the cost. But secondly, a second alternative, we are not replicating, rather you are splitting the hardware into smaller pieces. These are called stages, very nominal cost increase. But one thing is required which you have not considered. You see, you consider the washing example. Suppose there is a washing machine, there is a dryer. Suppose washing machine has finished with a cloth, but dryer is not yet ready, it is still drying the last cloth. So, that cloth has to be temporarily put in some kind of a tray or a buffer. So, there has to be some trays between the machines which can temporarily store the clothes before it can be fed to the next machine. Okay. So, this is the need for buffering. So, we need a tray between washing and drying machines and between drying and ironing machines. So, in the same way, when we talk about a hardware pipeline, we need a latch or a register between successive stages which can store the latch, store the values before it can be processed by the next stage. This is how a hardware pipeline will look like. So, a total computation I am dividing into k number of stages S1, S2 up to Sk. There are latches between the stages and there is a clock. Clock is activating the latches. So, what is the purpose of the latch? You see, when the first data comes, that data gets stored in this latch and S1 is working on that. After S1 has finished doing the computation, the result it will be storing in this latch. At the same time, the next data will be stored on this latch. So, when S1 is working on the second data, S2 is working on the result of the first data. Now, if this latch was not there, then what might have happened is that while S1 is working on the next data, the output could be changing. So, the input of S2 could also be changing, resulting in wrong computation. So, we are using the latch to hold temporarily the previous data, so that while S2 is processing the data does not change. Okay. Similarly, for the other stages, and this latches are typically master slave flip flops, which serve the purpose of isolating inputs from outputs. And the stages S1, S2 to Sk, these are typically combination circuits. We shall see examples later. Okay. So, when clock is applied, everything gets shifted to the right by one place. So, S1 goes to S2, S2 goes to S3, S3 goes to S4 and so on. So, when clock comes, data in a pipeline will move forward in a lockstep fashion. This is what really happens. Fine. Now, talking about the structure of a pipeline. So, a pipeline can look like this, as we have seen. It is called a linear pipeline. The stages are connected in a linear fashion. The output of one goes to the input of the other in exactly in a straight line fashion. But for more complex systems, of course, here we shall not be considering such examples. Pipelines can be non-linear also, meaning that there will be stages, let us say A, B, C, but data can flow not necessarily from A to B, B to C. Data can go from A to C also sometimes, C to B also, and C to A also. Okay. So, there can be multiple paths the data can take. For example, a possible sequence can be A, B, say A, B, C, B, C, A, C, A, then it comes out from this path. So, this can be a possible sequence of data computation, but these are for more complex cases, forget this for the time being. Now, you see these are some example pipelines. Now, how processing is carried out, this is depicted by a data structure which is called a reservation table. What does reservation table show? Reservation table shows the utilization pattern of the stages, like in the various time steps, how are the pipeline stages utilized. In time step 1, which stage you are using, in time step 2, which stage, in time step 3, which stage, and so on. This is depicted nicely in the form of a tabular fashion in the reservation table. Okay. Now, in the reservation table, the x axis shows the time steps and y axis shows the stages. The number of columns will give you the total number of stages, that means the evaluation time. Let us take an example of a 4-stage linear pipeline. Suppose I have a 4-stage pipeline where these pink boxes are the latches. The reservation table can be shown like this. These are the stages. So, in time step 1 you are using S1, time step 2 you are using S2, time step 3 S3, time step 4 S4. So, it will be a diagonal matrix kind of a thing, X will go like this. For a linear pipeline, the reservation table will always look like this, right. But for a non-linear pipeline, reservation table can be more complex, because as we have seen, for a non-linear pipeline there can be feed forward like S1 to S3 or feedback S3 to S2, S3 to S1, such connections. Let us say, suppose I am computing two functions x and y. Now, in the function x, my pipeline utilization can be like this. First the data comes, it goes to S1, then S2, then S3, from S3 it again goes to S2. You see, from S3 to S2 there is a path, from S2 again to S3, S3 to S1, S3 to S1 there is a path, and S1 to S3, S1 to S3 also there is a path, S3 to S1, and finally it finishes. From S1 there is a path for the data to go out. And similarly for the other computation y, say from S1 to S3, S2, S3, S1, S3 then goes out. You see from S3 also there is a path to go out. So, x computation the results are generated here, y generated here. But here I mean it is not very important for you to understand all these things, because the examples we shall be taking, they will all be the reservation tables for the linear pipeline. So, we shall only be considering linear pipelines. Okay. So, in a reservation table, multiple cross marks in a row means repeated use of the same stage in different cycles, like here S1 will be used in time step 1, also in time step 5. Contiguous x's in a row, suppose there are 2 x's side by side, which means a stage will be used for more than one cycle. Multiple x's in a column, it is not shown in the example, which means more than 2 stages may be active at the same time step. Okay, fine. Let us look into some simple calculation. So, for a pipeline, what you have said very loosely is that if there are k number of stages, we expect our speed up to be approximately k. Let us see how it comes, right. So, some notations, let tau denote the clock period of the pipeline, Ti is the time delay for stage Si. Let us say we consider a pipeline like this, we have stage S1, S2, S3 and so on, and there will be latches in between the stages. So, I am assuming that the time to compute S1 is T1, this is T2, this is T3, this is T4 and so on, right. So, Ti is the time delay of stage Si and let us say dL is the delay of a latch. So, what will be the total delay of a stage? T1 plus the delay of a latch, right. So, the delay of this will be T1 plus dL, delay of this will be T2 plus dL and so on, right. Now, you see we are having a common clock. So, we will have to look at which stage is the slowest. We find out the maximum of Ti, call it tau m, and tau m plus the latch delay, that will be the clock period of the pipeline. Clock period cannot be less than this, and the pipeline frequency has to be reciprocal of that. Like let us take an example, suppose I have a pipeline with 4 stages where the stage delays are let us say 10 nanosecond, 12 nanoseconds, 8 nanoseconds and 14 nanoseconds, and the latch delay is let us say 1 nanosecond. So, what will be the maximum clock frequency? Here my tau will be max of the delays, which is 14 plus the latch delay 15. So, my clock frequency can be 1 by 15, so many gigahertz, because these are in nanoseconds, right. Fine. So, let us move on. So, what will be the total time that will be required to process n data sets? You see there are k number of stages in the pipe, right. So, k minus 1 time steps will be required for the pipe to fill up, and after the pipe has filled up, there will be one output generated every clock. So, k minus 1 for the pipe to fill up, after that one output every clock, there are n data sets. So, for all the results I need n clock cycles after that. So, you see k minus 1 plus n whole into clock period, this will be the total time taken to process means to process n data. But if we assume that we have an equivalent non-pipelined processor where we did not use pipeline, then the time taken would be T1 n number of means n into tau, where means n is the number of data and k into tau we are assuming is the time to process every data. So, we are ignoring the latch overheads. So, approximately it will be n k tau. So, the speed up will be the time taken on this processor divided by the time taken on the pipeline. So, it will be like this, tau cancels out like this, and as I said, as n becomes large, so you can ignore this k as compared to n and this 1. So, it becomes n k divided by n approximately k. So, speed up will be approximately equal to k, and pipeline efficiency is defined as Sk divided by k. You see, k is the maximum possible speed up and Sk is the actual speed up. So, you see your actual thing is k minus 1 plus n, right, into tau, k minus 1 plus n, and this is n. So, if you just divide it up, this is defined as the pipeline efficiency. But pipeline efficiency equal to 1 means you are having an ideal value of k, and pipeline throughput says that how many operations are completed per unit time. You are processing n number of data items, you are taking a time Tk. So, n divided by Tk will be number of operations per unit time, n divided by Tk. So, these are some simple calculations, and this actually shows you the speed of curve. Let us say number of tasks n. So, as you plot speed up versus n for different values of k, you will see that your curve looks like this. For k equal to 4, your speed up increases, but it levels to 4. So, as n increases, it goes approximately to 4. For k equal to 8, it approaches 8. For k equal to 12, it approaches 12. Okay. So, this k is the maximum speed up that can be attained in a pipeline. So, there are some other issues like clock skew and jitter. You see, clock frequency does not only depend on the logic delay and the time you need to set and reset the latch. There are other times called skew, jitter and the setup time. Skew means the clock signal might get delayed on its way to the different flip flops and latches. Suppose you generate the clock here, you will have to deliver the clock to different points. The length of the paths can be different. So, there will be different delays that the clock signal will experience before it reaches the different flip flops or the latches. This is what is called skew, maximum delay difference between the arrival of the clocks, right. Jitter is, well, on the same latch sometimes there will be a variation in delay. Jitter arises due to environmental disturbances like noise in the power supply and so on. Logic delay we have already seen, the delay in the slow stage in the pipeline, that tau, and setup time we have mentioned this earlier. Setup time is the minimum time that you should make a signal stable at the input of the latch, so that the latch can accept it. So, not only the latch delay, you will have to add the latch setup time also to it. These are some small delays that get added. Okay? Fine. So, with this we come to the end of this lecture, where we just gave you an overview of what is pipeline, how it works, what are the basic principles behind it. So, now that we have seen what a pipeline is and how it works, in the next couple of lectures we shall give you some very simple examples of pipelines and illustrate how we can actually code these designs in Verilog, how we can implement this designs in Verilog, and through simulation we shall see that actually it is working in a pipeline. Thank you.